Hi, physics class. We've been working with vectors, and specifically in 2 dimensions, and how do we add vectors together. We saw we added them head to tail, and we got a resultant vector. And we also talked about breaking those vectors down into their components. So if we had a vector at an angle, we could break it into an x component and a y component. We're leading up to how do we understand 2-dimensional motion. And we're going to broach that subject today. We're going to get to that point today. But first, I want to do a quick review and do some things on the grid. We're going to show a couple situations here, and I'm going to build to the point where I can help you understand what I mean when we're talking about 2-dimensional motion. And we're doing a very specific case of 2-dimensional motion, that being the case of something we call a projectile. And how does a projectile fly through the air? So let's get going. Let's do our first scenario here. We're going to have a very simple one. We're going to have a deer where it's got a velocity of 5 meters per second due north. Now, typically, if we're talking about something moving on the surface of the earth, kind of like if we're looking at a map, we'll have north be our vertical axis, our positive part of our y-axis, and we'll have east then be the positive part of our x-axis. So if our deer is moving 5 meters per second north, then we would draw our vector right here on our y-axis, because that's north. Now, in this case, our deer's got a velocity of 5 meters per second. I made each little grid line here 0.5 meter per second. So there's 10 grid lines here we're crossing. So what's our velocity in the x direction? What's our velocity in the east direction? Well, there's no velocity component here in the eastern direction. So we're going to say that our velocity in the x direction is 0. Well, if the x direction is all 0, that means all of our motion's in the y direction, kind of what our picture tells us. Pretty easy to break down a vector into its components when it's running right along one of our axes. All right, let's get a little bit more complicated. Let's move it so it's not directly across one of our axes. Let's put our vector over here. There we go. So there's our vector. Our deer is running at 5.7 meters per second and then 45 degrees north of east. Now, north of east, that's the way I've been trying to get you guys to learn how to calculate angles. We're talking about the positive x direction. That's our east vector. 45 degrees north of east means we're rotating towards the north direction, which is the way we would normally count our angles. Right? So this would be a positive 45. So if we're going to break this down to an x and a y, we're just going to draw our vectors down and across. What's our vector for the across part here? There's our x component, right? We just kind of draw our line straight down here. That's where our x component is going to end. Draw a line over here. This is where our y component is going to end. That's a quick way to break our vector into x and y components. How do we do that mathematically? Well, if we look at it, here's our angle. Here's our angle here. What's our adjacent side here? That's our x, right? So our adjacent, if we know the angle, we know the hypotenuse being 5.7. We know our angle being 45. How do we figure out our x component? It's simply our hypotenuse times this cosine of 45 degrees. Now tell us that the magnitude of our x component is 4. Now, some of you may have caught that the 45, that's a special angle. And in this case, it's nice because the cosine and the sine are the same. So this guy's going to have also 4 meters per second north as its y component. Really easy to see, and you can see the lines here. We can measure them all out. But to find our component, well, remember, all we need to do is we take the magnitude of our vector, and we multiply it by the cosine, or the sine for the x, the sine for the y. And this is as long as we're measuring our angle from the x-axis. Okay. Let's look at another situation here. Let's make it so it's not such a nice angle. 18 degrees is not one of those nice angles. Well, let's draw a vector out here. I can get it to show up. There we go. So our deer is running at 3.2 meters per second, and it's running at an angle of 18 degrees north of east. That's the way we normally want to measure them, right? Where the east is our 0. We're going north. We're going in a positive direction for 18 degrees. So what's our magnitude of our x here? Right? Our x, remember, that's our horizontal component. That's going to be our cosine of our angle here. So we're going to take our magnitude, 3.2. We're going to multiply that 3.2 meters per second times the cosine of our angle, cosine of 18. And we're going to see that our x component is 3 meters per second. Same with the y is pretty easy as well, except we're using sine of our angle this time to get our y, and it's going to calculate out to be 1 meter per second. All right. Now I want you to look at this one. because we're going to compare it to our next scenario. Here we have 18 degrees north of east. So this little angle here is 18 degrees. In our next problem, we've got 72 degrees north of east. So we're way north of east. We're way up here. Some of you that are good in geometry might say, well, if you're at 72 degrees north of east, that's also saying 18 degrees east of north. So very similar to our last problem, we just kind of rotated our triangle around. Right, so instead of being almost horizontal, this one's almost vertical. Right, but the angle is still the same. We just kind of switched them around. If we look at our x component, right, our x component, 3.2 meters per second is our magnitude. We're going to multiply that by the cosine of our 72. We're going to see it's 1 meter per second. Now, I've gone through great lengths to kind of hint that it's very similar to the last problem. All we did was flip our angle around a little bit, so hopefully you're catching on that our y is going to be 4 meters per second here. I'm sorry, 3 meters per second. 3.2 times our sine of 72. The angles are very similar. They're just respect to different axes. In situation 3, it was with respect to the x-axis. Situation 4, that 18 degrees is with respect to the y-axis. That's why we're seeing some of the similar numbers. But typically our standard is we're going to measure things with respect to the east axis, to the x-axis, and that's why this one now is 72 degrees north of east. All right. Now I want you to look at this. We're 3.2 meters per second times 72 degrees north of east. What happens if we double our magnitude of our velocity? Well, if we double the magnitude of velocity, 6.4 meters per second, I'm hoping you can see by just looking at the way we calculate our x and the way we calculate our y, what's different. The only thing that changed, we saw the same angle, the only thing that changed is we doubled our magnitude out here. So if we multiplied our magnitude by 2, we're going to multiply our x component by 2. So instead of being the 1 before, it's now 2. And similar with our y component. Last time it was 3. We doubled our magnitude. So we're going to double our y component. So we can scale. We call that scaling a vector. We multiplied our last problem, situation 4, we multiplied it by 2. Didn't change the angle. All it did was change the magnitude. And we could do the same thing with any vector. Multiply it by 1, 2, 3, 4, 2.5, 3.9247, whatever scale we want, right? It's just a number. It's scaling things up or down, making something bigger or larger by a set amount, a set proportion. And we can definitely use that when we're doing vectors. Now, on a side, I had talked about adding vectors before. I should have added this piece in. I want to take a moment to do it now. If we multiply by a negative number, what does that do? That literally just flips our vector around. If you think in a normal one-dimensional case, right? If we're at the origin, we move forward positive 3, our arrow went to the right. If we move forward negative 3, our arrow would go to the left. Right? So if we subtract a vector, that's the same thing as adding the -1 times that vector. Well, it means we just flip our vector around. Now let's move on to situation 6. In the previous ones, we had our x-axis and our y-axis being north, south, east, west. Notice I don't have them here. The reason we're doing that is because now we're going to define our y-axis, our vertical axis. That's our vertical direction. And our x-axis will still stay our horizontal. So anywhere in our horizontal plane, we're going to do the same kind of math. It doesn't matter which 2 dimensions we're choosing. So if you look at this is very familiar to what we started off. I think it was a problem 2, problem 1. No, 1 was 5 meters per second north. No, we didn't do one totally similar to this. We'll roll the ball across the floor at 4 meters a second. So here we go. Let's draw our vector out here at 4 meters per second. Kind of like what we were doing before in the first few problems. V of x, that's our magnitude, 4 meters per second. We're going to multiply that by the cosine of 0, that's 1. And hopefully that makes enough sense too. If it's rolling along the x-axis, all that velocity is going to be along our x-axis, and there'll be 0 velocity in our y-axis. It's not going up or down at all. Let's make this one a tad more complicated. Let's move on to another situation. Instead of having our bar rolling horizontally across the floor, let's pick the ball up. We're going to be 15 meters above, almost kind of like what we were doing in the football stands earlier this year. The instant that we drop that ball, is it moving at all? No. It has no vertical velocity. It has no horizontal velocity. Right? So we're not going to have any x or y components. Now notice here I have Vx, and it's just the x. For the Vy, I've added the subscript I for initial. We know that even though it's not moving up or down when we first let go of it, we know it's going to start falling. It's going to start moving. So we know that our initial velocity, even though it's 0, our y velocity is going to change. It's going to keep going faster and faster the longer we go. But we're only talking here about the beginning right now. What's that instantaneous when we start things off? In both cases here, we're just going to draw a dot because we had no velocity in our x direction and we had no velocity in our y direction. Okay. Again, key, we're talking about just the initial velocity for our y here. Let's make it a little bit more complicated. So instead of just dropping the ball, let's throw it horizontally. So this would have been like if we were up in the bleachers in the football stadium, and instead of just dropping it, we would have backed up a few feet and rolled the ball so that it fell off the edge, and then we would roll it at 4 meters per second. Well, here it's telling us we're rolling it horizontally. So if it's rolling horizontally, we know that it's going to have an x component, right? That's what that means. It's rolling horizontally. And that's the only motion it has. At the second we release our hand, or the second it falls off the edge of the bleacher, it's only got a velocity in the x direction. It has no initial velocity going up or down. It's not until after it falls off the edge that it's going to gain a velocity in the y direction. So our initial velocity here is simply 0 meters per second. Okay. And notice the height doesn't come into play here at all, just it's above the ground. Can we make that a little bit more complicated? Yes, let's take one more step. So instead of the first one, we just dropped the ball. The second one, we rolled the ball horizontally. What if instead of that, let's throw it straight up? Well, if we throw it straight up, what does that mean? That means our ball's initial velocity is all in the vertical direction. It's all positive. It's got no component in the horizontal direction. So our Vx is going to be 0 here. But our Vy, our initial velocity in the y direction, that's going to be the 4 meters per second that we threw it with. Let's put these together now. Let's instead of just rolling it horizontally or throwing it straight up, let's throw it at an angle. We're going to make it about as complicated as we can get for 2 dimensions. Let's do the 45 degrees angle and 5.7 meters per second. Now what I want you to notice is we did this back here in slide 2 for our deer in the XY plane, in the map plane, if you will. Now we're doing the same thing in our YZ plane, our vertical horizontal plane, our YX plane, or make it vertical this time. It's the same math. It's the same algebra. It's the same geometry. All we're going to do is we're going at 45 degrees. There's our vector. 45 degrees above the horizontal. There's our 45 degrees measured above our x-axis. And we're going to throw it with a velocity of 5.7 meters per second. This is the same thing that we did in problem number 2. What's our velocity in the x-axis? We can project it down, right? Let's take our arrowhead, drop it all the way down to our x-axis. There's our magnitude of our x. Let's take our arrowhead over here. Let's project it over here. That's the magnitude of our y. But I want you to see the math is the same. We got that 5.7 meters per second for our magnitude. We're going to multiply it by the cosine of 45. We're going to get 4 meters a second. Same with our initial velocity in the y direction. Again, it's initial. We know it's going to change. It's also going to be 4 meters per second. This is exactly the same math that we did in that second example that we did here today. This leads us into the beginning of what I want to talk about of two-dimensional motion, and specifically a subclass of that we're going to call projectile motion. The horizontal component of an object's motion is not affected by gravity. Right? If we're rolling a ball across the bleacher, gravity's not doing anything to that ball because gravity can only accelerate up or down. Right? So the horizontal component of our motion is not affected by gravity. Friction, yes, but gravity, no. The vertical component of our object's motion is definitely affected by gravity. Right? As soon as it leaves that bleacher, there's bleachers not holding it up, it's going to start falling down. So the vertical component of an object's motion is definitely affected by gravity. So what do we call this? This kind of motion I mentioned a second ago, we call this projectile motion. Almost think of like a cannonball being shot out of a cannon. It's a projectile. A projectile is an object upon which the only force is gravity. We can ignore wind resistance, we can ignore friction, we can ignore wind, we can ignore currents. It's just saying the only force on that object is gravity. In this particular case, if we're talking about a projectile, the horizontal component of a projectile's velocity remains constant. Remains constant. There's no force to change it. There's no force, there's no F equals ma, no force equals mass times acceleration, no acceleration. And we'll learn more about that particular equation later on, F equals ma. But there's no horizontal component. There's no change to the velocity in our projectile's horizontal component. The vertical, though, we do have a change. The vertical component of a projectile's velocity does change over time. And why does it change over time? Because gravity is causing it to accelerate in a negative direction. It's causing a negative change to our velocity. So this is what I mean about projectile motion. Tomorrow we'll do a little bit more work and doing some calculations about projectile motion. It's nice because we can do some things. We got some zeros in here that'll help us make our problems easier. And we've actually touched on problems like this already this year. Now I'm just formalizing it for you. All right, guys, have a good one. Thanks for watching. Stay tuned for continuing this tomorrow. Take care, guys. Bye.